Okay, good afternoon. Let's start lecture. Okay, let's continue on the partial derivative. Okay, so we'll finish the partial derivative today. So in the previous lecture, we learned about what a multivariable functions are and how do we take a calculus of multivariable functions. So given a, let's say for example, a function of two variables, so that's a multivariable function. Okay. If we're interested in the partial derivative of f with respect to the x, and this will be the definition. Okay. So in other words, this basically represents it's the rate of change of function f. Okay. And given a change in x. So that's basically what the partial derivative is. Okay. Yeah. Now based on the definition, as you can clearly see, when you take a partial derivative, with respect to x at here, and the y is not changing, so the y is kept the same. So basically, when you take a partial derivative function f with respect to x, you will treat the y as if it's a constant here, right? Yeah, so that's the whole idea of partial derivative. Okay, how you can treat the other variables as a constant when you're taking this partial derivative. Okay, so let's take a look at a couple examples. Okay. Giving a multivariable function f of xy, which is described by this function right here, and we wanted to verify we want to verify this this equation is valid. Right. So this essentially is a second order differential equation, but it's a partial differential equation at here. Okay. Yeah. So let's take a look at this one here. What do we need to calculate? We need to calculate a second order partial derivative with respect to x, another second order partial derivative with respect to y. So let's just start with first order partial f over partial x. Okay. At this stage, the way to write it properly is very important. Okay, basically, for example, I'm looking at the partial f over partial x, and I can write it like this because I know my f is this, so I can put everything in a big bracket. Okay, so this could be if you want to write, then you better write it this way here. Because you know why? Because I've seen so many times the student when they take a partial derivative, without writing this, just write this one here, and then they start to equal, for the rest of the things here, right? And technically it's not right. And also it's very dangerous. You could make some mistakes if you don't write it properly. Okay. Okay. Now, before we move on at here, for this tan inverse function at here, maybe just to basically review it here. If we have a function of a single variable, okay, so if we take a derivative of this function with respect to u, and we get 1 plus u squared, 1 over 1 plus u squared. Okay, yeah. So for single variable, you would get this. Now the only difference here is this is instead of u, this is y over x at here, right? Okay. So let's let u equal to y over x. Okay. We do that. This actually requires a chain rule, simple chain rule, which I'll summarize a little bit more details next. Okay. Then this partial f over partial x, okay, can be written as, now when you let the u equal to y over x, so if you replace the y over x with u, then a function f is just a function of u now. So we can write it as df over du and partial u over partial x. So you see the way I write it here. The first one here is not a partial f over partial u, because when you replace the y over x with u, it's a single variable function, right? So that's a straight df over du. Then partial u over partial x. So that's the simple chain rule set here. So df over du is basically this term here, so that's 1 over 1 plus u squared. And partial u over partial x, now this is where you need to fix the y as if it's a constant. Then you get y over negative x squared. Okay. Good. So that's the first order partial derivative. Substitute the u back over here. Okay. Yeah. Make sure you do some simplifications before moving on. So the simplifications, I say this is x squared here. The simplifications, if you are not too sure, you can always write it one more step here. So this is x squared over x squared plus y squared, and then negative y over x squared. X squared cancel. You got a negative y over x squared plus y squared. Okay. So that's the first order derivative, partial derivative. Okay. Okay, the tricky part is the second order partial derivative. You keep doing another partial derivative. Basically, this means you're taking another partial derivative for the results, okay, with respect to x again. So technically speaking, you're doing this at here. Okay. So make sure when you write at this stage, try to write down all the informations, right, all the expressions correctly. Okay, then for this partial derivative, again, you need to make sure that you're treating the y as if it's a constant. Okay, so it's like any constant, right? Over x squared plus the constant square. Okay, yeah. So you can use either a product rule or quotient rule at here for this derivative. Okay, if I choose to use say the quotient rule at here, for example. Okay, so I have a negatives at the top, in the front at here. Then the bottom here becomes x squared plus y squared. Okay, so this is basically like a u over v, right? Quotient rule. Bottom here is v squared. And then at the top here, right? So the quotient rule basically says, okay, like this. Okay. Well, except that the u at here is y. So when you take a derivative here, you're not taking y's derivative. What you're taking is partial y over partial x, basically, right? Yeah. But y is what? Y at here is a constant, isn't it, right? So your first term, the y prime, or partial y over partial x, is 0. Okay. So the first term here is 0, and then the second term here times 0, 0 times anything is still 0, right? So that basically naturally is gone. Okay. Yeah. So then we're left with. Oops. We're left with the second term here, which is y times negative here, y times the partial derivative of the bottom with respect to x. And the partial derivative of the bottom with respect to x is 2x. Okay. So finally, you can simplify negative and negative, cancel each other. You get 2xy over x squared plus y squared squared. Okay. So this process here needs you to be very careful. Which is a constant? Okay, which is a variable? What variable are you taking partial derivative with respect to? Right. So that's what you get for the second order partial derivative. And then you can try the similar approach for the partial derivative with respect to y, and you end up with negative 2xy over x squared plus y squared squared. Okay, yeah. So this similarly, you'll get this one here. So apparently, these two terms adding each other give us 0. So that equation at here, okay, is verified. Okay, so this is valid. Okay, yeah. Now this equation at here, okay, so this equation at here is a very important equation actually. Okay, so this one here is called the Laplace equation. Okay, and this is Laplace equation in 2 dimensions. So it's only with respect to x and y, and you can easily expand that to a Laplace equation in 3D. Okay. So that's a 3D format for Laplace equation. Okay. Yeah. If you later when you learn in heat transfer, fluid flow type of topics here, wave propagation, okay, or even in physics, quantum mechanics, you will see the Laplace equation. Okay, so it's a very interesting equation there. Now, for this one here, you can actually define. Okay, it's just this on the side note here. You can define an operator. You can define an operator here as this guy here, and actually we'll come to that today here. This is called a del square. You can define an operator. Okay. So that operator, you can use it to operate on any functions. So if you put it in front of f, then you get this Laplace equation at here, same thing. You can put it another function w, and you get same Laplace equation, but it's just a different function now, right? Yeah. So that's an operator here. This operator is called a Laplacian. So that's basically a different format of a differentiator, actually. Okay. Yeah. So we're going to learn pretty soon today this operator here. We're going to learn this guy here. Okay. It's called basically it's a gradient operator. It's called a del. Okay, so we'll learn this shortly. Okay. In this case, we have this del square. All right. Yeah. Okay, so that's an example. How would you carry out the partial derivative? Where you have to be careful with. Okay. Yeah. So let's take a look at one more example at it here, and then we can summarize a few product rules and chain rules. Okay. Okay. given a function like this, given an equation like this. So this is the equation. Okay? So we try to find what's partial z over partial x. Now this one is quite different from the previous one. The previous one, you ask for what's the partial f over partial x, but that one you were given a function f already, right? Yeah. But in this case, you don't have the function z, so basically you don't know what the z function is. But you're just beginning an equation in here involving the x, y, and the z, and asking for this partial derivative. Okay. Yeah. So in this particular case, what we can do is, okay, we'll take a partial derivative with respect to x on both sides of this equation in here. Okay, on both sides of the equation. It's like taking derivative of both sides of a single variable function. So, just first order derivative, second order derivative, like that type of things. Okay, so now always keep in mind you're looking for partial z over partial x. Okay, it's like you're thinking, okay, so z must be a function of x and y, right? Yeah. Then in this case, you're going to treat the y, right, as if it's a constant. Okay, yeah. So now for the for the expression here, I can write it. Okay, one more line in here. Basically, I can expand the bracket. Okay, like this, right? Yeah. So I can expand the bracket like this. Okay. So this is much clearer now because I can deal with each one of the term in here by making some really quick calculations. Because we're treating the y as was constant, then this term must be 0, right? And then this term here is a partial derivative of x, is actually basically a derivative x, so that basically is 1, right? Okay. And then over this side here, you have this partial over partial x, y, z. You're treating the y as a constant, so this y can be taken out of the bracket, and you're left with partial z over partial x. So perfect. So this is what we're looking for, right? Finally, it comes out of the all the mass set here. Okay. And then this one here, same thing. You're taking partial derivative of this ln z over x. Okay. Essentially, it's like another chain rule here. You can let the u equal to ln z, right? A derivative of u is 1. Ln u is 1 over z. So in this case here, you write the 1 over z first, and then partial z over partial x. Okay. So now you have explicitly all the partial z over partial x expressed. So simplify this. And then solve for partial z over partial x. 1 over y minus 1 over z. Okay. So it's a slightly different type of example, how you can get the partial derivative based on an equation here. But you got to also be careful here. This one works, but not necessarily it always works. If you are given completely different expression here, the way that it operates here may not necessarily actually will give you an answer for partial z over partial x. Okay, so but that's one way to try it though. Okay. Any questions so far in terms of partial derivative? Okay. Okay, so let's summarize some chain rules. Okay. Related to the partial derivative. Okay. Some of the rules I write it down, but honestly speaking, oftentimes when you are calculating or when you're computing partial derivative, not necessarily you're actually, following the rules. You're actually, maybe you're just acting naturally, following it. You're not explicitly writing down to follow it, right? Okay, so there are different cases for chain rule. Okay, different cases of chain rule here. So let's take a look at the first case here. If we have a function f of x, y, okay, and x is function of t, and y is also function of t. Okay. Yeah. So now if we are looking for df over dt, okay, so this is essentially a chain rule here, but you don't necessarily have to follow the chain rule though, right? Because if you sub the x of t into the function, sub x and y into the function here, and then the function f ultimately is just a function of t, right? So that's why you can write it as the df over dt at here. But if you use a chain rule, so this will be the how you use the chain rule here. So partial f over partial x first, and dx over dt, partial f over partial y, and dx over dt. Okay. Yeah. So that's the chain rule here. Whether you really need to use the chain rule or not, it's probably not necessary. But that's how you would sometimes if function f is a very complicated function of x and y. So maybe this way actually will simplify the computation quite a bit. Alternative writing will be just like this, right? So this is actually I'm going to use this expression quite use this one here just shortly for teaching the grading vectors. Okay. If you have a function of 3 variables, and all you need to do is just add a term in here at the end. Okay. Yeah. Okay. That's the first chain rule. Second case of a chain rule here. Let's see if I'm still going to use the function 2 variables for illustration here. Then x instead of function of t is a function, another function of another 2 variables. So x is function u and v. Yes. Oh, sorry. This is y, right? Yeah. Good point. Yeah. Okay, so let's take a look at the second case. For this type of multivariable function, and x is another function u and v, if we're looking for is partial f over partial u, okay. See that if we're looking for partial f over partial u now, then the chain rule here will be partial f over partial x, and then partial x over partial u. Okay, yeah. It's quite different from the writing is previous straight here, right? Now this is a partial now, and then partial f over partial y over partial u. Okay. So that's the second type of chain rule, right? You can try what will be the partial f over partial v. Right? It's very simple, right? So just try yourself. Just one little thing at here I wanted to point out is that you look at the first case set here, not the probably not this one. Let me give you an example like this, single variable. So let's see if I have a single variable here. Okay, that's a single variable, right? And then if we're looking for df over dt, you can do df over dx and dx over dt, right? Yeah. Okay. Yeah. Okay. So in this particular case, if you look at this single variable here, you can do what? you can mathematically you can cancel out these terms, right? Yeah, and then you get basically the same thing on the left and the right, basically. Okay, yeah, make sense? Yeah. Now coming back to this chain rule here, okay, for the multivariable function. So I have a partial f over partial x over partial u, and then partial f over partial y, and partial y over partial u. So you might be attempted to do what? To cancel this, isn't it, right? So you look at that, well, isn't that this same symbol? Maybe I can cancel that, right? I said you attempted to, but then you can't, okay? The answer is you can't do that, okay? So basically, there's a fundamental difference. You look at this one, so you can do this, but then you can't do this, right? Yeah. So then what's the fundamental difference here? Basically, this partial x, okay, this is different, okay? Fundamentally, basically, it's different from this guy here. Okay. And how different? How different is this one actually exists? Okay. So basically, if your target exists basically in the space, okay, here's a dx. You know, that's something you can tell people. This is a dx that exists. Okay. But this one here, so it technically it actually doesn't exist. Okay. So it's not a real quantity. You can't actually cancel it, basically. Okay, it's a mathematical symbol, essentially. Right? So that's something you got to be careful with here when you deal with this straight D and a partial D. Okay, so the straight D, right? So this quantity is called a differential, right? Okay, it's called a differential. Differential basically is an infinitesimal small quantity. Okay? But the partial x here, it's not a differential. It's just a partial x. That's it. Okay. So that mainly the chain rules here probably just the two cases at here. You can extend from the case 2 from function 2 variable to 3 variable. Really no difference at all. Okay. So the main type of chain rules are the two cases at here. Okay. Yeah. So let's take a look at an example. Okay, here's example here. This is something that you might actually will be reviewed when you're taking EMAT course in the 3rd year for electrical students. Okay, basically, you know, we typically deal with the Cartesian coordinates, but then you are also aware that there are different ways of describing a point. So aside from the Cartesian coordinates, there's also polar coordinates, right? Yeah. So for example, this is a Cartesian coordinates at here, okay? And you can use a coordinates x, y to describe the location for this point, for example, A at here, okay? Yeah. But alternatively, you can also describe this location A, use another set of parameters or variables. So you can also use, let's say, r and theta, right, to describe its location. So the r and theta here is what we call the polar coordinates. Okay. So yeah. Now the difference is, for example, when you have Cartesian coordinates at here. Okay. So you have x and y coordinates. Okay. So you have I hat at here and j hat at here, right, representing the two coordinates. Okay. For polar coordinates, you also have a similar way of labeling a coordinate system for the r and the theta. Now, if you think about the way the theta goes, so theta always goes what? It's rotating, right? It's always rotating, and r always goes what? Always goes out of the center here. So I can indicate using an arrow here, this one here indicates this is a, let's say if I have a unit vector in the r direction, just like the unit vector I hat in the x-axis direction. So I can use this unit vector representing the direction of r change. And I can use another unit vector here, let's say I call it e theta hat, representing the change for the theta direction, right? And these two are perpendicular to each other, just like the x and y, or j hat and I hat are perpendicular to each other. So that coordinate system here, so this red one here, you can call it, this is a polar coordinate system. Okay? Yeah. So then there's a intricate problem now. There's a conversion called transformation, basically between different coordinate systems. You know, when you have a one point specified in one coordinate system, then the same information. So then how do you describe the same thing, same point, in a different coordinate system, right? Yeah. The end results may look different, but they actually describe the same points, right? Yeah. So that's the idea here. This partial derivative, okay, and it can give us actually that type of information, right? So let's just try this example right here first, okay? First of all, let's say partial f over partial r. The idea essentially, you know, if you look at partial f over partial r, so the same function can be expressed using either x and y or using r and theta, right? Same function, okay? Yeah. This is where we can use the chain rule. So the partial f over partial r, okay? So this one here, suppose you start with f of x, y. And apparently it's very straightforward. Is your relationship of x, this is r cosine theta, and this is r sine theta, right? So that's how you relate the Cartesian coordinates to the polar coordinates. X equal to r cosine theta, y equal to r sine theta. Okay. Then the chain rule here is basically partial f over partial x first, partial x over partial r, plus partial f over partial y, and then times partial y over partial r. Right? So that's the simple chain rule, like what we just illustrated, right? Which one is it again? So that chain rule is actually the second case, right? The second case here. Okay, so you do this calculation. The question didn't give you the function f(x,y), so we can keep this partial f or partial x here as it is. But we do know what the x is. X equal to r cosine theta. So the partial x over partial r is cosine theta. Then partial f over partial x. And plus sine theta. Partial f over partial y. Okay. So that's your partial f over partial r. Okay. Yeah. Now what about the partial f over partial x? Okay. Yeah. So in this case, then this is more like your f is given in terms of r and theta, and you're looking for the partial f over partial x. Okay. Yeah. So use the same interchain rule. So this time is partial f over partial r over partial x, and then plus partial f partial theta over partial x. Right. Okay. Same chain rule. Okay. Same way of applying the chain rule here. So r, in this case, r is a function x and y, and theta is a function of x and y, like this. Is that good? Yeah. So now this one here is a bit of a tricky now. The question give us is x is a function r theta. That's great, right? So x is a function of r theta. Y is a function of r theta. This is a given, right? This is why it is so easy for us to calculate the first one here, partial x over partial r and partial y over partial r. Okay, but we don't have this function r in terms of x and y, or theta in terms of x, y, right? Yeah. So we have to do a little bit of digging in here to find that relationship. Okay. Yeah. So oops. Good. Okay. Okay. So let's see how can we find that relationship here. It's very simple. Okay, if you look at the original relationship here, what is R? R is basically what? Square root x squared plus y squared, right? And what about the theta at here? Okay. The theta here, if you look at theta, tan theta equal to what? Y over x. So theta equal to arc tan y over x. So that's your expression for r and theta in terms of x and y, right? So now we can calculate, continue from the chain rule here. We'll keep the partial f or partial r, but calculating partial r over partial x. So maybe I'll just write it separately. So what is partial r over partial x, right? Okay. And this is the typical partial derivative. When you're taking partial x r over x, you treat the y as if it's a constant. Okay. So 1/2. Okay. That's your partial r over x. So simplify this a little bit. We get x over x squared plus y squared. Okay. And you can further simplify this a little bit here. Okay, further simplify this. This is r cosine theta, and the bottom here is r, so that essentially is the cosine theta. Okay. Yeah. Yes. Where is it? Left. This one here? Am I right or am I wrong? On my right. Well, this is on your right, right? So, is it here? Other side. Why is it r cos theta? Well, x equal to r cosine theta, isn't it? Oh, why doesn't it have r now? Oh, because this is a partial x over partial r, right? And you treat the theta as a constant. And so the r is gone, isn't it? Yeah? Okay. We gotta get our left and right first, right? Okay. So let's continue here, right? Yeah. And finally, you take partial theta over partial x. So again, that's actually very similar like this tan inverse y over x, like the example we just did. Okay. So the derivative theta over x. Okay. You can use the same analogy there. You get negative y over, okay, negative y over x squared plus y squared. And then the y is r sine theta. Bottom here is r squared. So the overall is negative 1 over r sine theta. Okay? Yeah. Okay, so once we find these two, we can simply substitute back here and here. Okay. And I can get the partial f over partial x now. So that's cosine theta times partial f over partial r plus, well, this is minus now, minus 1 over r sine theta partial f over partial theta. Okay. So that's your partial f over partial x. Good? Okay. So I want you to try yourself. What's the partial f over partial y? Okay, so just try yourself. So the relationship here essentially, when you have a different coordinate system, taking partial derivatives back to the corresponding coordinate system variables, and that's basically how you would be able to juggle between all of the different things here. Okay. Yeah. Okay, so I think I'm going to skip that example. The other one is, I think this is a very straightforward chain rule, not as complicated this one here. Okay. Yeah. Any questions on the chain rules? No? Good. Okay, so let's continue at here. The next concept here called the total differential. Okay. So I'm going to have to approach this concept through the same function of single variables first. Okay, through very simple ideas. Okay. So let's say I start with the function of single variable. And here's your f of x here. So we learned if I start with x at here and increase the x by delta x, okay, then we'll be probably interested to know, okay, basically what's the change of the function f when you change the x from x to x plus delta x, right? That's a very simple question when we learn the function single variable here. Okay, so and of course delta f equal to the function of f at x plus delta x minus the value of the function at x location, right? So subtract each other, you get the delta f. Okay. Yeah. But often in time you don't do that calculation. You probably what you do is you do a so-called approximation, right? How you can approximate this change of f when there's a change in x. So how do we approximate then? So to do the approximation, one way to do it, as we learned, we can use a straight line here, right, to do the approximation basically. Okay. Yeah. The straight line approximation, basically what it do is we create a tangent line at this x equal to x location, okay, and then we use this little portion here, right, to represent the approximated value delta f. Okay. Yeah. Now, this is a straight line tangent here, and this value here, as we all learned, this is representing the slope, right? It's basically the derivative of the function with respect to x at this location, and increasing by delta x. So this portion is delta x at here. Okay. So bottom line is that delta f can be approximated, right, using the derivative of this function over respect to x, or the slope at here, and then time that small distance delta x, right? Small distance delta x. Good? Yeah. So the way to write this one here is, basically often in time we write it probably, let's say, okay, so this is y, let's see, how can I write it here, okay, this is, let's say, dy over dx equal to, okay, or df over dx, doesn't matter, okay, or equal to, the way you write it, okay, the derivative, right, f prime of x, right, okay, yeah. But see, now if I write it slightly differently here, okay, so I'm going to write it like this right here. I write df equal to f prime x times dx. So I'll write it like this. Okay. Yeah. So whatever here is the derivative with respect to x. right? So maybe coming back to this one here a little bit here, okay? Coming back to here. So you can approximate the function f, the change of function f, using the slope or the derivative times delta x. That's approximate. But if delta x really approach to 0, so or the second location is so close to the first location, then that's not going to be approximate sign anymore, right? That's going to be basically an exact equal sign. Okay. What's the exact single equal sign? That exact. So the delta here, when this go to 0, the delta will become a straight d basically. So you see the straight d, delta becomes straight d. So this will become a df. So that's basically become this guy here, right? Basically become this. So the df equal to f prime times dx. Okay. Yeah. Just trying to reinforce the idea of the derivative here. Now this df here, this guy here is called a differential. I mentioned this quite a few times. This is called a differential. So infinitesimal small quantity, right? Okay. Yeah. And this line that we're approximating at here, right? This line here, okay, that's a line equation. It passing through, let's say, a certain location of a with a derivative of a, and then right minus a. Let's say if this is a location, right? So that this is basically you use a line to approximate of the curve f of x, okay, at x equal to a location, right? So that's function single variable we learned before. You know, you have all of this very simple things, right? Very simple things here. But just trying to extract the concept out a little bit more specifically. Okay. Yeah. Now let's extend it to function of two variables. Okay. Yeah. So now let's see. Think about the function two variable now. Let's see if I have function two variables. And let's see. I'm going to draw something in here. Okay. Yeah. Okay. Suppose you're initially at x0, y0 location. Okay. Yeah. And we're gonna basically we're gonna go from the x0, y0 location, let's say, to somewhere else, maybe to another location, x and y. All right? Yeah. So let's say we go instead of xy, let's put it x0 plus delta x and y0 plus delta y. Okay. So you go from one location to another location. Okay. Now, this is a given function f of x, y. So for this particular function, as we learned, okay, this can be represented by some type of a surface, right? So this is your f of x, y at here. Okay. So now you look at the way it goes here is, okay, initially you're here, so that's the corresponding. This is your f of x naught, y naught location, right? Okay. And after the movement, and you're here now, so this will be x naught delta x and y plus delta y naught plus delta y location. Okay. Yeah. Is that good? Okay. So very similarly, I ask the same question. So as you go from here to here, and the value for the function f change from here to here, right? Okay. So then you basically you're talking about here. Okay, if I'm interested in the delta f value, okay. So what's the rate of change? What's the change of the function f value as we move from here to here? That make sense, right? That's the same question we asked there, right? Okay. Yeah. And of course, you can calculate the function value here minus the function value there. You get the exact change of function f. Okay, yeah. But if I use the same thing, I don't want to calculate the exact value. I want to use approximate approach. Okay, approximation approach. Okay. So like this one here. So this one to approximate the point here with a straight line, then you go from here to here. It's like as long as you go along the straight line from here, then you get the delta change for the function f, right? Yeah. So now coming back here, what can we do? What can we, if I use the same inner approach, what can I use to approximate the change from here to here? Or even, see that part of curve in a 2D function, single variable, you approximate it using what? Using a single straight line, right? If this is a surface, and take a guess, what can I use to approximate the change, or to approximate this portion of a surface? For curve, I use a straight line. Then for surface, what can I use to approximate this portion of a surface? Line and what's the other one we learned? The plane, right? So if I can approximate the curve here, use a straight line, then from within a small range here, I can probably approximate from here to here using, it really depends on the drawing, using a plane, right? And that plane will actually be tangent to this point here. Okay? So I can use probably a plane to approximate this part of the surface. And then the delta f, I can, instead of calculating the actual delta f, I can calculate the delta f change, okay, basically along that plane. It's like the delta f change along the straight line, right? Okay. So now, then the question is, what's the plane equation, right? You know, the other one you have the line equation. And what's the plane equation? Instead of answering what's the plane equation here, so maybe maybe what we can do is, okay, first let's write down something actually you learned. What's the Taylor series for f of x, y, okay, at x naught, y naught location? Okay. Yeah. So when you have a function of two variables, a single variable, you can expand it using Taylor series expansion. When you have a function of two variables, you can do the same thing. You can also expand the function of two variables using Taylor series expansion. So the way to expand it is this. So f of x, y is equal to, okay, expanded at x naught, y naught, equal to this. And then fx here, okay, x naught, y naught, x minus x naught plus fy here, x naught, y naught, y minus y naught, okay, and then plus those higher order terms, okay, Taylor series expansion. So that's Taylor expansion for this function f at here. Is that good? Yeah. You can try to recall the Taylor expansion for single variable. So I'm not writing the high order here. I'm only writing up to the first order. Okay, up to the first order. Then, if I get rid of all the high order terms, okay, get rid of all the high order terms, then the equation basically become f of x, y is approximately equal to this, and plus fx, x naught, y naught, okay, x minus x naught plus fy, okay, x naught, y naught, y minus y naught. Okay. Yeah. If you get rid of all the higher order terms, basically. Okay. Yeah. Is that good? Right. Okay. Let's look at this expression in here. Okay. Let's look at this expression. Okay. So basically, your function f is approximately equal to this. Okay. Now, from this single expression here, I can extract two informations here. Okay. One information is I'll move this term to the left side there. Okay, to the left side. Okay. Then from left side, when you move this to the left side here, so you have this value of function f at the current x, y location. minus the initial location, right? Which is what? Which is basically delta f. Okay, basically delta f. And so delta f is approximately equal to fx right here at the initial location okay. So that's the first thing I can extract based on the Taylor series expansion. Yeah. So my delta f is approximately equal to this chunk right here, right? Equal to this chunk. Now, before we move on in here, we're almost at the total differential concept now. Let's get back to this Taylor series expansion, right? Only look at the right side. Only look at the right side here. Okay. Look at the right side. If I look at the right side here, I'm going to let's say, a new variable, okay, L, equal to the whole right side. Equal to the whole right side here. So what we just defined here is what? We just define ourselves an expression like this, right? Okay, a new function, a new multivariable function L of x, y. Okay. So this side here is like a z. Okay, so like a z equal to a whole expression, a long expression in terms of x and a y. Okay, you plug x, y value here, you get basically a z value, right? Get a z value here. Okay, so this is a partial derivative with respect to x at the location x naught, y naught. This is a partial derivative of f with respect to y at the location x naught, y naught. So if you take a very close look at the bottom expression here, right? Now this is constant, isn't it? Right? This is constant. This is also constant. Okay. And this is like the z value, and this is also constant. So what does this format remind you? The format of the writing here. What type of shape does it remind you here? Well, what does it describe basically, right? A plane, exactly, right? So you have a coefficient for the x, coefficient for the y, you have a coefficient for the z, which is 1, and you have a point that goes through at x naught, y naught, and the z naught location. Right? It's a plane. Okay? And the plane has some normal vectors which is given by the x, y, z coefficients. Right? Yeah. So this is the plane. Now remember what I said, you can use a plane. You can use a plane to approximate the surface at x naught, y naught location, right? Yeah. Now that is basically a plane at here. Okay? Yeah. And we're using the plane to approximate that part of the surface. It's a tangent plane, and we can actually use basically, you see that the expression for this delta f here. That's pretty much the plane equation except the first term, isn't it? Right? Yeah. So delta f is basically the value from here minus this. Okay, for this side here. So that's the delta f here. It's basically like the single function, single variables. You approximate along that straight line. This one here, you approximate the delta f change along that plane, right? Along the plane. So along the plane, how much change there is used to approximate the function f change as you're moving from here to here. Is that okay? Yeah. So having said all of this here, coming back to total differential, let's look at this delta f change for function 2 variables here. Okay? Yeah. Now, if I plug in x, if I let x equal to x naught plus delta x, and then y equal to y naught plus delta y, right? That's the change. So plugging here and here, what's the delta f here? Delta f is equal to approximately to fx times delta x plus fy times delta y, right? Okay, so you plug it here and here, you get this expression here. So that's approximate, right? That's approximate. Now, if we let delta x go to 0, delta y go to 0, okay, so infinitesimally small, close to the original point, then this is not going to be an approximate sign anymore, right? And the delta will change to what? Straight d, right? Delta will change to straight d. So this expression will become df equal to fx dx plus fy dy. Or partial f over partial x dx plus partial y, f over partial y and dy. Now this one here is what we call the total differential now. Okay, this is called total differential. Okay. So differential originally that for single variable differentials, df equal to the derivative times dx. That's for single variable, right? Function single variable. When you have function multivariable or two variable in this case, okay, then it's called not a total. It's not a differential. It's called a total differential because the change of function f value depends on both the change in the x and the y direction. So that's why you see here we have both partial f with partial x and partial f with partial y added here. Okay, yeah. That's total. That's what basically we're looking for, the total differential. It's very simple, you know. If whatever I'm trying to end up with this results that here is too confusing to you, then in terms of results, all you need to memorize is this simple formula here. Okay, this is for function single variable. If it's three variable, then you add another term. So in this case here, what's involved? You only need to calculate this partial derivative and this partial derivative, and then you put it here and here. That's your total differential formula, basically. Is that good? Yeah. Okay. So if I have a function three variables, then you can easily extend that, okay, by adding a term. Okay. Now, all you have. The other thing is we're going to look at an example right here. Okay. So the other thing is where the total differential comes from. It comes from basically this guy here, right? Comes from this guy. Okay. Now this guy here is actually more applicable. It's a concept of to approximate the change of function f when you have a change in the x and y direction. Okay. Yeah. And what does this involve? It involves this two partial derivatives here. Okay. And you also have to know this delta change in the x and y. Then you can calculate delta change in the f function direction. Okay. So these two here, okay, they're not exactly the same, but they're very much related to each other. Okay. Yeah. So I'll give you a quick example right here. This example can be related to an example we did just at the beginning of the lecture there. Okay. So here is function fxy. Okay, this example we did, right? Can you find its total differential df? Okay, what's the total differential for this function f at here?
Is that the tan of negative y over x?
Yeah, so inverse tan basically. Sorry, inverse tan y over x. Okay. So that's example we did. In that example, what did we do? We're trying to show that this function satisfies this Laplace equation, right? Okay. Yeah. Now, in this case, I'm trying to calculate the df. I'll write the formula again. So that's your total differential formula. So what do we need for this formula? we need this, right? Yeah. Now if you look at the example we did, we actually already calculated these two partial derivatives. Okay, so we calculate this one here, the partial f or partial x equal to negative y over x squared plus y squared, and this one here equal to x plus x squared plus y squared. Okay, so basically asking for the total differential, this is the result. Okay, that's it. Don't forget to write down a dx here. So I noticed in the past some students somehow think that dx dy are redundant. This is a part of formula. Okay, you have to leave it there. You have to leave this as the part of formula here. Okay, yeah. Not getting rid of it like just partial f or partial f plus partial f or partial y, right? Okay, so what's more applicable is the type of example as following here. Okay, yeah. So let's say we have a cone in here. Yes. So suppose we have a cone. The cone has, of course, has a bottom, has a radius. Has a radius r, and it also has a height h, right? You can use r and h to calculate its volume, which is 1/3 pi r squared times h. Okay. Okay, so now let's say consider this scenario. Suppose that the r goes from 10 centimeter to 10.1 centimeter. The h goes from 1 meter to 0.99 meter. Okay. And we want to, what will be the corresponding volume change given the change in the r and height h? Okay, yeah. So this is basically an application of this concept of total differential here, right? The total differential. If you look at this total differential here, now this is the total differential, but it actually can be used, okay, if you expand that little dx a little more, it'll become a delta x, right? And then you can use it to approximate the change in the function f. Okay? Yeah. So let's say this is how we will approach this one. So delta v is approximately partial v over partial r times delta r plus partial v over partial h times delta h. Okay. So let's say here, what's delta r, what's delta h, or what is partial v over partial r? So that's all the pieces we had to figure out right away, right? Okay. Partial v over partial r, maybe I'll just partial v over partial r, let's write it separately. Okay. So here's your v here, 1/3 pi r squared. So your v is a function of r and h. You keep the h as a constant. So 2/3 pi times r. And then times what? H, right? Times h. And what will be the partial v over partial, what is it? Partial h, right? So that's 1/3 pi r squared. Good? Okay. So how does it change? So this is basically coming back to the question here. Where is the initial point? This is very important. You have to be very clear where is the initial point, where is the final point, right? So in this case here, maybe I say Where is the initial point? R naught, H naught is where? 10 and 1, right? So maybe 1, let's change that to centimeter, so 100 centimeter. Okay. Then, how does it change? So the R goes from 10 to 10.1 centimeter. So that basically, that tells me that delta R equal to what? 10.1 minus 10, which is 0.1 centimeter. And H goes from 1 meter to 0.99 meter. So the delta H equal to 0.99 meter, but 99 meters is 99 centimeter minus 100 centimeter, so negative 1 centimeter. Okay? Yeah. This is the part often in time people will make a mistake at here. Okay? Yeah. So you always use the current value minus the original, right? Yeah. Now coming back to the two partial derivative, right? The two partial derivative. Now, two partial derivative, I had to show you again the original basically here. You see the original here, when we calculate the delta here, what's the partial derivative? The partial derivative is calculated at which location? At the x naught, y naught location, which is the original, right? So then in order to calculate this two partial derivative, we need to plug in the r naught, h naught location. Okay? That's how you would calculate this two partial derivative. Okay. And we already have r naught labeled as a 10 and 100 centimeter. So you need to just plug it into this two here, okay, and then you do the calculation. So I think I can put it back together, okay, into this approximate change. So 2 over 3 times pi, r is 10, h is 100, and then delta r is 0.1. Second one here is 1/3 pi times 10 square times delta h, which is -1. Yes?
So we're using the R naught value instead of the R1 value just because we have to? Or is there any way that we could use the R1 value?
No, this is strictly prohibited because of how the formula is derived here, right? Yeah. And you see the Taylor series expansion here. Whenever you expand around a certain point, x naught, y naught, which is initial points, right? Yeah. And that's how you calculate your derivative. Basically, everything is built upon your initial location. Yeah, so the plane is tangent to the initial position, or in terms of single variable, the line is tangent to initial location. Yeah, very good. Okay. So, plugging everything, you can use your calculator, and then you get 100 pi over 3 centimeters cubic, centimeter. Okay. That's the typical question. Then the last question in the assignment number 3 is a very similar question. Basically, okay, so basically you have two resistors connecting in parallel, and we wanted to calculate a change in the total resistance. Okay, when there are changes in the R1 and R2 here. So R1 changes from 20 to 20.1, and R2 changes from 25 to 24.9. Right? So when you have a change in R1 and R2, what will be the approximate change in the resistance R at here? Right? That's the last question there. Okay? So that's a very direct application of the total differential concept. So basically, you need to calculate the two partial derivative, and you need to calculate the delta change in R1 and R2. Okay. You put things together, and you get the approximate change in the delta R. Okay? Yeah. So there are two different ways of doing it, but mostly I would recommend to use a very straightforward way here. Write down the R function, okay, as it is. So this is your parallel connected resistors. That will be the total resistance for the network of resistors. Okay. Then from here, you have two variables, x and y, or R1 and R2. So now you can calculate partial R over partial R1 and the partial R over partial R2. Okay? Yeah. So maybe I'll just calculate 1 in here. Okay? So what is partial R over partial R1? Use the quotient rule. So this is R1 plus R2 squared at the bottom here, and the top. So if this is R1, R2, this is U, then the partial derivative with respect to R1, you will end up with just R2. Then times V, so R1 plus R2. Then minus R1 times R2 times the partial derivative at the bottom with respect to R1, which is 1. Okay? So that's the partial derivative, right? Okay. So simplify this a little bit here. You get R2 squared over R1 plus R2 squared. Yeah. So you can stop here. You don't actually because then you can substitute R1, R2 value at here, right? Initial values 20 and 25. Okay, like this. Okay. But delta R1 equal to 0.1. Delta R2 equal to what? Negative 0.1. All right? Yeah. Any questions? Okay. The reminder, midterm next week. So no lecture next Tuesday. Just cancel it out because the time we'll use it for the midterm. Okay. And I will be in my office during the lecture time. If you have questions, feel free to come. Okay. Otherwise, I'll see you next Wednesday evening at 7:15 in the 5th building. All right. Tutorial. I think I'm gonna cancel 2 because Monday there's no tutorial, and